Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students at Illinois State University, please go to smarturl.it/help ISU actuary. Today I'm posting a practice problem for exam LTAM, long-term actuarial models. This is a problem from the last spring 2018 exam MLC. It covers material that is still on the exam LTAM. Problem number 6 from multiple choice section. A single premium 10-year term insurance policy with death benefit of $100,000 is issued to a 40-year-old person. The benefit is payable at the moment of death. You are given the single benefit is single premium simply is $31.44. In fact, it doesn't say that it's a benefit premium. I shouldn't have said that. It says the single premium. Whatever role this premium pays, it's not relevant because we'll just be calculating, as you'll see, the loss at issue. Mortality follows the illustrative life table. Deaths are uniformly distributed over each year of age. So separately over each year, not overall. This is the UDD assumption, not the Moivre assumption. And the interest rate is 4%, which is not the interest rate in the illustrative life table. So we can't look up the single benefit premiums for life annuity or life insurance in the table. We can only look up mortality data. Calculate the probability that the present value of the loss at issue is more than $75,000. And here's the solution. The present value of the loss at issue is $100,000 benefit paid if the person dies at time t for t less than or equal to 10, and so it's 100,000 times the present value factor, 1.04 to the negative t, or minus t, and then minus the single premium paid up front of $31.44 if the person dies, so for t less than or equal to 10. And then if the person lives throughout the policy, the present value of the loss at issue is negative $31.44. Just the premium paid is collected. The company has a gain of $31.44. Well, in general, this L is a decreasing function of t. Now, it becomes flat for t greater than 0. It becomes constant, but before that it's decreasing. So the longer the person lives, the smaller the loss. And of course, the loss is the biggest if t is 0, the person dies instantly. Also note that when the loss at issue equals exactly 75,000, we would have 100,000 times 1.04 to the minus t minus 31.44. That would be equal to 75,000. We can actually solve this. So if you move 31.44 to the other side, you would get 78,144. Divide both sides by 100,000, and the right-hand side becomes 0.78144. Then, since the unknown t is in the exponent, take the natural logarithm of both sides and then solve for t, and you would get that t must be equal to minus natural logarithm of 0.78144 over a natural logarithm 1.04. Notice that this natural logarithm of a fraction in the numerator is negative, so putting a minus sign in front of it will make it positive, and this comes out to be approximately 6.2879251. Okay, so if the person dies earlier than this age, the loss will be bigger than 75,000. Basically, that's what we conclude. And the probability of that is the probability that the person dies, a 40-year-old dies within 6.2879258 years. which is 1 minus the probability of survival. Why am I doing it with the survival? Because survival calculations can be done using the illustrative life table with the LX function, the size of the cohort, and it's a little bit simpler this way to calculate. So what we have is that probability is simply L 46.2879251 over L40. L40 is in the table, but the fractional age like that is not. But under uniform distribution of deaths, this is simply a linear combination of L46 and L47, because this is in between 46 and 47. So we basically do a linear interpolation between 46 and 47. This 0.2879251 is the fraction of the age that we have already traveled towards the age 47, so that's L47 is multiplied by that, and we are in a sense still remaining in that fraction 1 minus that at age 46. That's roughly the idea of linear interpolation. Under uniform distribution of deaths, linear interpolation is exact under UDD. Okay, and now we can look up in the illustrative life table L46 and for L47 and L40 and plug it in and then do the calculation, and then comes out to be 0.97883882, and what we're looking for is 1 minus that, the probability of dying within that period of time, and that comes out to be 0.02116118, and that's answer E. Please remember this is copyrighted material. The problem itself comes from the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.